Hi there. So what I'm going to be doing in these videos is trying to more or less replicate what a normal lesson experience might be like. So you can see over down to the reverse camera. So down there, there's some questions. I'll provide some definitions, a bit of a discussion, and then end up going through the questions that are there. So we're just going to continue on from where we left off from term 1 with the function concepts. So of course we know there's different types of functions, right? There's graphs of straight lines. Remember, you can visually check the vertical line test will indicate whether it's a function or not. We've got quadratic functions, right? Like parabolas. Again, passes a vertical line test, so it's a function. What else? We got other higher order polynomials, which is kind of like a quadratic in that it's got some curvy bumps, but still this passes vertical line test. It's a function. And then we've got things not to do with, not all functions have powers of x, right? We've got functions like this, which you might recognize as an exponential. And again, this is a function as well. So there's a few kind of common features that we can use to describe or find for all these different functions. One is the intercepts, where it passes the y-axis or the x-axis, and the other one is going to be domain and range, which we'll discuss after intercepts. So looking over at the first question to the left, we've got the function f of x equals 2x plus 4. So I'm just going to write this first as y equals 2x plus 4. So we should all recognize that this is a straight line graph with a y-intercept of 4 and a gradient of 2. So just to kind of visualize it, it's going to look something approximately like this. So here it's got a y-intercept and an x-intercept. So if I ask you to find the y-intercept, you'd substitute in when x equals 0 into the equation. Y equals 2 times 0 plus 4, which is 4. So that's going to be the y-intercept over there is 4. And then if we were to find the x-intercept, well, the x-intercept is when the y value is 0. So we'd say, let's calculate when does y equals 0 in this equation. Well, it's when 0 equals 2x plus 4, which if we solve this equation, minusing 4 from both sides, and dividing both sides by 2, we would get this x-intercept here is -2. So I'm just going to do the exact same thing now. The only difference is that we're going to start to use function notation, right? So instead of saying when x equals 0, well, we still are going to say when x equals 0, but we're describing our function as the output is given by 2 times whatever you input and then plus 4. So like we just did over there, when x equals 0, well, we can write this, the y-intercept is going to be f of 0 when we put x equals 0 into the function. Right, so going to do the exact same calculation, we're just going to use function notation. Here's our function, we're going to put 0 as our input, and when we calculate it, we're going to get the exact same thing, 4, and so that would be the y-intercept. Similarly, any x-intercepts, well, x-intercepts are going to be similarly to like we just wrote when y equals 0, well, they're going to be whenever the function f of x equals 0. So we'll write an equation where our function equals 0. So in this case 2x plus 4 equals 0, and then again we'd solve it the the exact same way. So no new skill here other than just using different notation. Alright, so this time I'm going to go and do question 2, which you can see is a quadratic function, and this time I'll just use the function notation. Okay, so we've got our function is 2 times whatever you input and square it plus 10 times the input and then subtract 28 from it. Alright, so we can find the y-intercept by finding f of 0, so inputting 0 into this equation. 2 times 0 squared plus 10 times 0, both of them are going to be 0, and then if we minus 28, then we'll get the y-intercept is negative 28. Okay, and then where are the x-intercepts? Well, they are when the function equals 0. So we'll write f of x equals 0, and then f of x here we can replace with our function here in yellow. So our function is when does 2x squared plus 10x minus 28 equal 0, and now we'll solve this equation. So you might notice that they're all even, so we can divide throughout by 2 to simplify this a bit. X squared plus 5x minus, whoop. If we halve it, it's now 14 equals 0. Now we could use quadratic formula. I mean, we could have used quadratic formula before, but it's probably easier to just check if we can do this with a product and sum. So product of negative 14 and sum of 5 will work with 7 and negative 2. So we can factorize this to x plus 7, x minus 2, and then using null factor law, right, if two things are timesing together to give 0, either the left one has to be 0, the left factor is 0 when x is negative 7, or the other factor is 2, right, and so these are the x-intercepts. Okay, so of course any equation so far we've done in the course, we could need to find x and y intercepts, which would consequently help us graph this. So in this case, we could sketch this. We know that the x-intercepts, it passes through negative 7 and 2. This will be a bit out of proportion, and a y-intercept of negative 28. So this is a parabola that's going to look something approximately. Sorry, it's a bit of a sketchy sketch, but it's going to look approximately something like that. Okay, so far in these two examples, we've looked at a linear function, a straight line, if I can zoom out, and a quadratic function, a parabola. So with functions, these two functions have something quite distinct about them in terms of the values you can input and the values you can get out of the function. So if you look up here at the straight line, is there any restriction on what x value you can put into this equation? Well, you can put any x value you want into this equation, right? You can put x equals 0, 1, 2, 3, a billion, negative 17.5, right? You can put any x value you want into this equation. And if you look at the straight line, well, what type of output values can you get as the y value? Well, you can get positive numbers, 0, negative, right? You can get basically any number from negative infinity to infinity in the other direction that you can input into the x value and get out from the function. Now the difference with the quadratic function is that you can put in any x value you want, right? 2x squared plus 10x minus 28. You can put in any x value you want. Pick an x value, right, on the number line anywhere, and you can put it into that equation and find the corresponding function value, right? The y value on the graph. However, the difference here is that there is a restriction on what y values you can get out. You can get, for example, the y value is 0 or some positive numbers, and you can get some negative numbers, but now negative 28 isn't the lowest value, but there is some minimum, right? Down the bottom of the graph, there's some lowest value that at the turning point that you can't get past. You can't get, for example, negative, assume that vertex isn't lower than 50 or so. You can't get, say, negative 500 or negative 2317. Those values you can't get as a output. When you put, there's no number you can input into the function and get the number negative 2317. So this idea of restrictions on the inputs and outputs are called the domain and range. So I'll define them here. So the domain of a function is is a word to describe all the, be good if the pen would write, yep, all the possible input values, and usually it's of a function of variable x, and the word range is basically the same thing, describes all the possible output values. So think of this of like on your graph, what are the different y values you can get on a graph. Okay. So to be able to describe these, we're going to introduce something called set notation. So I think this will be easiest if I draw up a picture. And set notation we'll use for functions, and we'll use it later in a probability topic as well. So, for example, let me just draw a graph here. Right, so this graph that I'm drawing has is a function. It's got unique output values for every input value. It passes the vertical line test. Okay, so here I'm using closed circle to indicate that this straight line graph goes all the way down to -3 and includes -3, and then it goes up to here where x is 2, and open circle, just like when we're drawing an inequality on the number line, means it doesn't actually equal 2, but it can be things less than 2. So for here, the domain is all the possible input values. So what values can you input into this function and get something on the graph? Well, you can put anywhere from x equals -3, right, including -3. You can put -2, -1, 0, 1, 1.5, 1.7, all the way up to 2, but not including 2. So we can say the domain is, you can write this as an inequality. It's everything x is bigger than or equal to -3, and or x can be less than 2, but not including 2. So that's how we could write this as an inequality. However, how we're going to write this is with what's called set notation. So we're going to still do the exact same thing, but we've got some symbols that actually make it a bit shorter to write this. So we're going to say x, all the x values are in. So this symbol is called the element symbol, and it means you read that x is in. Right, this is the element symbol. X is an element of the set. We're going to go from -3 to 2. So kind of like writing a coordinate, right? We're writing two different values with separated by a comma, but here the -3 is the lowest value, moving up to the 2 is the, sorry, that's around the wrong way. The -3 up to 2 and we can use a square bracket to indicate we're going to include -3, and an open bracket that says don't include 2. So this says anything bigger than or equal to -3 or anything less than 2 is the x values you can input into this function. Right, so very similar to what I just wrote as an inequality, but this is a bit kind of neater and quicker to write. Right, so we'll just this means includes 3, and the close bracket excludes 2. Alright, so similarly for the range now, we've got what values? We've got all the y values from here. They're from the lowest y value is 1, and we're including 1, so we're going to put 1 with a square bracket, and up to the highest y value is 5 with an open bracket. Right, so this says the range, what are the possible output values of this function? Well, along the y-axis they go from 1 up to 5, including 1, but not including 5. Okay, so now I'm going to go along the side and do all the domain and range of the questions there. So here we've got, for question 3, f of x equals mx plus c, so you'll recognize that as a, hopefully, as a straight line. It's arbitrary, it doesn't have actual values for m and c, but it's just 1 power of x, and m is the gradient and c is the constant, that's the y value. So I mean, we can just kind of sketch something to visualize these. Right, it's going to be something along those lines. So for the domain, for any linear function, just like the one I did earlier up the top, x can go, well, where can it go from? Like I discussed before, it can go all the way down to -infinity and all the way up to infinity. Now, whenever we're going to write -infinity or infinity in a domain or range, right, because it's just something conceptual and not an actual value, we can't actually get to -infinity and include it, so we're always going to be doing open brackets there. And similarly, the range, what are the possible output values? Well, they go all the way down to -infinity and up to +infinity as well. Now, this is something unique just to this, going from -infinity to infinity, is there's a bit of a quicker way to write this. In mathematics, there's different types of sets of numbers. So for example, you know, when you're a kid and you learn to count, there's the counting numbers, which we refer to as the natural numbers, right? They're quite natural. You just get some objects and you count them, and so they're called the natural numbers, and there's a symbol n with some extra lines that means just the numbers 1, 2, 3, 4, 5, 6, 7, 8, etc. off to infinity. Then there's other sets of numbers. There's the set of integers, which is positive and negative whole numbers and 0. There's a few different types of just kind of very common sets we interact with, and one of these is called the real numbers, right? Which is what we've just looked at here, all the numbers from -infinity to +infinity. So, or we could write both of these as x is in the real numbers. So real numbers is an R with, it's like a double stem on the R. So this says x is in the real numbers, which means the exact same thing as from -infinity to infinity. So either one is fine to write. But as you can see, it might be quicker to just write any more that come up in these examples I've written. I'll just use x is in R because, you know, in maths we like to be efficient, and it's quicker to write that than to write that. Okay, 4. f of x is x squared. So again, if you know what these graphs look like, you might like to draw up a little sketch. So x squared is going to be a parabola that looks something like that. So what's the domain along the x-axis? Well, what values can we put into here? I already said this up above about the other quadratic we looked at. You can put in any x value you want, right? There's no restriction on it. You can put in x equals 0, 1, 2, 3, up to infinity, down to negative infinity. So D for the domain is x is a real number, any of them, all infinite of them. Now what about the range though? What is the lowest number you can have down here? Well, you can have 0, but then what output values can you get along the y-axis? Well, you can get anything up towards positive infinity. So the range goes starting down at 0, and for x squared, can we get 0? Well, yeah, when we put in 0, 0 squared is 0. So the range is going from 0, including 0, up to positive infinity, but we're again going to do open bracket whenever we do infinity. Alright, next, 2 to the power of x. So you'll notice here that 2 is, the variable x is in the exponent. So this is an exponential graph. So that's like, when I draw up the top of the page, it's going to look something like that. And it's going to have an asymptote down towards the x-axis. So again, the domain is what possible x values can we put into the function? Well, there's no restriction. You can put x equals 0, x equals 1, x equals 2, up to infinity. You can put negative numbers in, you can put decimals. You can put any x number you want into this function. So x is in the real numbers, or from negative infinity to infinity. Now what about the range though? The range is very similar to the parabola above. What values output from this function along the y-axis? Well, you can get only positive numbers. We don't go below the x-axis. They go all the way up towards infinity. And they do come down towards 0, but because there's an asymptote there, it never actually equals 0. There's no x value you can put into 2 to the power of x and actually get a value of 0. So this time, very, very similar to the parabola above. It goes from 0 to infinity, but because we're not including 0, it can't actually get to 0. The range is going to have an open bracket for the set with 0 there. Okay, 6. You may recognize this as a 1 over x. When x is in the denominator, it's a hyperbola. Whoops. Okay, and so a basic hyperbola, 1 over x, if you don't know, looks like that. So you can do this kind of by just analyzing and looking at the function and thinking about what numbers you can put in, or you can sketch a graph to visualize it. So here, what x value can't you put in? Well, if the equation is 1 over x, x is in the denominator, so that means we can't actually have because x is in the denominator there, x can't equal 0, can it? Can we put any other x value in? Any positive, negative number? Sure. So we're going to need a way to write this. So the domain, we can have anything from negative infinity all the way up to 0, but not including 0. And we can also have everything starting from 0, not including to 0, all the way up to positive infinity, right? We can put in any x value we want, along the negative side of the x-axis, and any value we want along the positive side of the x-axis. However, we can't actually put in 0. Now, what we can do is write, okay, well here's this one section of the domain, here's another section of the domain, and then we can combine them together. Just kind of, there's a mathematical symbol that very closely resembles the word and, so what are the domain? It's this bit and this bit, and the symbol we use for and, sorry about that, is a big U looking shape, which is the union symbol. Right, so when you form a union, you unite together and you combine them together, right? So when we've got two sets and you want to combine them together, this set and this other set, then we use the union symbol, big U looking shape. Sorry, getting ahead of myself. And then we've also got the range. So similarly, with the range, what output values can we get? Well, we can get any positive value from 0 up to infinity, or any negative value, 0 down to negative infinity. But again, we can't get 0. Because we've got 1 on the numerator, 1 over any number we put in is always going to be a number. It's not going to ever be, because you need to put 0 on the numerator to get a fraction with that equals 0. So because it's already got 1 on the top and not 0, then we're never going to get the number 0 as an output either. So the range will be the exact same from negative 0 to 0, unioned with 0 to infinity. Alright, so f of x equals root x minus 4. Now you might not know what the graph of root x minus 4 looks like. So this is where, like I was saying with the previous one, you might need to actually look at the function and have a think about what values you can put in and what values you can or can't get out. So what do you know about this? Well, underneath a square root we need to have a positive number or 0. So what numbers can we put into this function? Well, we need to put in numbers so that x minus 4, we need x minus 4 to be bigger than or equal to 0. So if we add 4 to both sides of this inequality, x needs to be bigger than 4. So the domain will be from 4, and then we can put in any number above it, right? 4 minus 4 gives 0, and root 0 is 0, that's fine. 20 minus 4 is 16, root 16 is 4, that's fine. You know, 5 billion minus 4, we can square root that. Oops, I forgot to say x is in. X is in the set from 4 to infinity. Okay, so we've just said that x needs to be bigger than or equal to 4, so what's the lowest function value we're going to get? Well, the lowest value we're going to get is when we put 4 into the function. F of 4 equals root 4 minus 4, which is root 0, which is 0 squared gives 0. So the range, now I'm going to write this instead of y as f of x, which will become clear y in a minute. The range of values of f of x go from 0, including 0, and if we square root a number, you know, a bigger number, we're going to get a bigger number. So just like the input values go off to infinity, the output values will go there a bit slower, but they'll still go towards infinity as well. Okay, so the reason I wrote the range a little bit differently there as f of x rather than y is because just with the last one here we've got just some different naming. Instead of x as the input variable, we've got t, and in the function is called g of t rather than f of x. Okay, so you might want to in your head translate this as kind of like, well, this is the graph of y equals x squared plus 1, which is a parabola that's been moved up 1. So what's the lowest value you could get in here? Well, it's going to be let's first do the domain. Can you put in any number you want in here? Sure can. Any number, you can square it and add 1 to it. So the domain isn't going to be x, it's going to be t is going to be all the values from, t is going to be, t is going to be in the reals. Now for the range, what's the lowest value we can get? Well, the lowest value you can get for the t squared piece would be 0. So when we do g of 0, we get 0 squared plus 1, which is 1. So the range is going to be all the output values, and this time it's called g of t. All the values g of t are going to go from 1, including 1, off to infinity. Right, so the only slight difference there is that the parabola, right, it's still going to be the same as x squared plus 1, parabola moved up by 1, but just the axes are labelled. The input is t and the output is g of t. So we do need to be clear. If it's a function just f of x, you can use. Oh, I actually missed it there as well. You can use y because we assume standard notation is x-axis and y-axis. But if the function is a function of a different variable name of t, say, rather than x, and it's given a different name, then we should define the domain and range there differently. Alright, that's all for this video. Bye.